So with that, let's start looking at some of the properties of a Gaussian beam. So of course, one thing you're going to be interested in, because you're looking at Gaussian beams, is going to be the intensity of the beam. Now I have that whole expression for the amplitude, right? That's this expression. So to get the intensity, you basically have to take, this is E of rho of Z, you would take E star, right? So if I do that, because the entire phase is a complex term, that's going to disappear. So the intensity is basically the amplitude squared, right? So I'm going to write out the square of this amplitude term. So I'll say I, which is of course a function of rho and Z, is A naught squared omega by omega of Z the whole, omega naught the whole squared. And this exponential, it's not a complex exponential, that's why it doesn't disappear. But when you square it, you will have that 2. What does this term do to the intensity? It tells you how the transverse intensity varies, right? And you can see that while it is a function of Z, right, the form of this expression is the same irrespective of the value of Z. The form is exactly the same. So if you were to look at a Gaussian beam propagating, so again I'll draw that standard picture, irrespective of which plane you look at, you could look at any plane. At any plane, the cross section, let's say I took intensity versus X, is going to be a Gaussian shaped. What will change if I go to another plane is not the form, not the shape, but of course where the peak occurs, right? So if I'm at this plane where the minimum spot is, this is what I would get. But if I traveled further, the beam has diverged. So at this plane, what you would get is still Gaussian, but more spread out. And if I went to this plane, still Gaussian, but even more spread out. Okay. Remember, we started this whole discussion on the Gaussian beam by saying the plane wave isn't a practical wave because its wavefront spreads out to infinity. Cross section, its wavefront spreads out to infinity, which could only be true if it had infinite energy. The Gaussian beam, as you can see, it rapidly falls, right? So it doesn't spread out to, that high intensity doesn't spread out to infinity. But even here, it asymptotically goes to infinity at the, so it's never really that, even in this description, we're not saying really that the beam ends somewhere. The way I'm drawing it, it's actually, it's going to, if you look at this expression, it actually continues till infinity, okay? However, what we would be interested in is what's the power contained in a certain radius of the beam, cross section of the beam. I know that the beam has this shape. I know that even this beam tends to spread out to infinity, okay? But how much of the beam power lies in the extremities of the beam, right? That's what is of interest to me. So we are interested not always in intensity, but we are also interested in the power, okay? And how would we arrive at the power? Well, we would integrate this intensity equation radially, so from 0 to infinity, and if you do that, you will end up with this expression. Okay, I naught is nothing but this A naught squared. So it's the peak intensity. Now, it shouldn't be surprising that the expression that you have arrived at is independent of Z, because we are assuming here that as this wave propagates, there is no loss. So, if the wave had a certain power in one plane, it has exactly the same power in any plane as it propagates. The difference is, though, that power is spread over a different area, right? So, the expression you get is independent of Z, and in fact, you can consider this term that I put in brackets sort of as an area. So, if you were to calculate the power when the beam was at its smallest waist, could consider that the spot had an area of pi omega naught squared, right, and a peak intensity of I naught. And this power then gets distributed as the beam propagates. Sometimes you will see the intensity rewritten in terms of the power. Okay, so it will be in terms of this power oh sorry, this is squared here. There's a squared here also, I missed. Okay, so sometimes you'll see it written in this form, but what is really of interest is often the ratio of power in a beam of radius, let's say rho naught. So it's the ratio of power in a beam of radius rho naught to the total power. Okay, so you're finding out 1 over P, and you're taking now, you're calculating the power, but you're not calculating the power in the entire beam. Now you're calculating the power in a certain area of radius, a circular area of radius r naught, rho naught. Okay, so we were looking at the ratio of power in a beam of radius rho naught to the total power, and again, if you work out this expression, you will get this. Okay. Now, why is this important? We are always interested in building as efficient systems as possible. You don't want to generate a beam and then lose half of the power of that beam. You want to ideally always use all of the power of the beam. If I look at this expression for a Gaussian beam, ideally, if I want to use all of the power, since my Gaussian beam also actually goes to infinity, I might say, well, my optics has to be infinitely large to capture all of the power. But we know that unlike a plane wave where the power is spread uniformly from the center all the way to infinity, the Gaussian beam is not, the power is not distributed in that way. It's distributed according to that Gaussian shape. That means most of the power is lying at the optical axis. But we want to quantify that better, and this expression, this ratio that I've written down here, helps us to quantify that. So how would I use it? I could say this expression was arrived at saying what is the power in a circle of radius rho naught compared to the total power of the beam. So let's say, let's take the case where rho naught is equal to omega of z. Okay, what is omega of z? We've said omega of z, we consider the radius of the beam, and in fact I can give you a better definition now. It is where the peak power or the peak intensity falls to 1 by E squared, the intensity on the axis. Okay, so if I look at this is I naught, and then I'm looking at where it has fallen to 1 by E squared of I naught. That, let's say it's that, then I'll say this is what I call the beam radius omega. Well, this is 2 omega of z. Okay, there are different definitions because radius I could define, I could say go to I naught by 2. Take the radius at I naught by 2. That is also a definition of radius. But in a Gaussian beam, omega of z refers to where it has fallen to 1 by E squared. It's the radius at that value. Okay. So, let's say I take rho naught. I choose the radius to be this size. That means I'm only capturing the power in this region. I'm throwing away this power. We are discarding that. How much power falls in this region where rho naught is equal to omega of z? And if you substitute this into this equation over here, you'll see that 86% of the power of the Gaussian beam lies within this region. Okay. Now, suppose you had got a value 5%. You would then say this definition of radius is a pretty bad definition. I'm saying this radius, this gives me a size, idea of the size of the Gaussian beam, but I am saying what I call the size of the beam only contains 5% of the power. Then I would consider that to be a bad definition of the size of the beam, right? Omega of z, if I choose rho naught to equal omega of z, then I get 86% of the power. Now this, you might still say this is not good enough, right? It's still, you're losing 14% of the power, but this is the definition by convention. I could look at a higher value. I'll say let's take rho naught to be 1.5 omega of z. Right? And then you'll find 99% of the power lies within that region. Okay? So, you're not constrained to design your optics and say the equation tells me the radius of this beam is omega of z, so all my optics in the system will have radius omega of z. This just gives you an idea of the size that contains at least 86% of the power. Really, when you're designing a system and you're considering that a Gaussian beam is traveling through it, if you calculate the propagation of the beam through the system and you find out that its largest omega of z is say 5 centimeters, when you're picking your optics, you might say, well, I'll pick a optics which has a radius 10 centimeters, right? So, you would choose optics to be some x times larger than omega by z to ensure you capture more power, right? And this x times, we call this the safety factor. Right? So, you want the size of your optics to definitely be larger than omega of z. Okay, and the safety factor is usually at least 2. Okay. usually choose it to be at least 2 times larger than the largest omega of z in your system. Okay. The third parameter of interest, of course, is the beam radius. So we already had written out this expression in terms of omega naught. So again, let's just, I've said this before, but just to make it clear, we are saying at the narrowest point, the beam radius is omega naught, and 2 omega naught is called the spot size of the beam. This changes, omega of z changes as the beam propagates. So let's say at z equal to z naught, omega of z is going to be root 2 omega naught. And for z very much greater than z naught, I can neglect the 1. So I will have omega of z is equal to z by z naught. And I can consider this omega naught by z naught to be equal or to give me an idea of the divergence of the beam. Okay, so let's look at divergence a little closer. What do I mean by divergence? Now the Gaussian beam, as it propagates, it has a planar nature at z equal to 0. So the beam is planar at z equal to 0. Let's draw the optical axis. If I were to draw a line, you'd see that beyond a certain point, if from in this region up to this point, if I were drawing a straight line from the center of the optical axis outward, that is kind of going in parallel with the Gaussian beam at a distance, the outer edge of the Gaussian beam at a distance, that happens in this region. But for a particular distance, that doesn't happen. This is nothing but the beam divergence. This is roughly omega naught. This is roughly z naught. So the Gaussian beam does not have a constant divergence. If it had a constant divergence, that means I would draw the beam, one side of the beam spreading out like this, and if I looked at this, it would be nothing but a straight line, and I could say this is theta naught, right? If the divergence was constant, I could draw a straight line along the outer edge of the beam and define an angle theta naught. I can't do that with the Gaussian beam. Why? Because in this region, you can see that the difference between the straight line and the outer edge of the beam is going on changing. It's after a point that it becomes constant. What is that point? That point happens after the distance z naught. And what's the width? What is the radius of the beam where that happens? Well, I'm taking it as omega naught, I'm taking z naught, and I'm defining the angle in terms of those two parameters. Okay, so the beam divergence theta naught is omega naught by z naught. But if you remember, we had said z naught is pi omega naught squared by lambda. So I can replace that here. Okay. And often people want to write this in terms of beam diameters, so you might see it written like this, just to show that it's in terms of diameters. So look at this expression carefully. Theta naught is telling you what is the divergence of the beam, and the moment you use the word divergence with the Gaussian beam, keep in mind that the divergence is varying across the distance z naught. So that's one more pointer towards z naught. Z naught is the distance over which there is no constant divergence. After z naught, I can consider the beam to have a constant divergence. Okay. Theta naught gives me an idea of the divergence of that beam, but theta naught is not independent of the other parameters of the Gaussian beam. It depends on the wavelength of the beam and its initial spot size, omega naught. It's inversely proportional to omega naught. What does that tell me? If I had a beam with a very small omega naught as opposed to a beam with a larger omega naught. So this is omega naught. This is, let's call it omega naught dash, just to show it's different. These are two different Gaussian beams. And we're looking, something has been done. Maybe there's a lens over here. Something has been done so that the spot is occurring where we see it. And the spot where we see it for what I've sketched in blue, omega naught dash, is very small. And the spot for the red light is larger. And what should be evident from the figures is that I've done something, I've used some optics to focus down the spot very small. But in doing so, what has happened to the divergence? The divergence has increased. So here's an inherent trade-off when you're working with Gaussian beams. You may want to have a very, very small spot size. Let's go back to our example of the DVD player. How is the light picking off information from the DVD? Well, it's focusing a spot of light on the disc. If this is the disc and this is the spot of light that is focused, that means I can only have one bit of information in this area. So I'll have one bit of information there, one bit of information there, one bit of information there. How much data I can put on this disc is limited by the spot that I can focus to. If I took the same disc and I now said the spot is focusing to this region, well, I could put another piece of information here, another piece here, another piece here. You can see I can put much more information. So the goal in many optical systems is to get as fine a spot as possible. You want to focus it down as small as possible. But I don't do that without some cost. And the cost here is, if the spot is focused to a smaller and smaller value, its divergence is larger. Now you might ask, so what? I want to capture or store a lot of information or read out a lot of information, and I can do that if the beam size is very small. Who cares about the divergence? But remember, in the CD pickup, you had a lens, you had the disc, and you were focusing onto this. Okay? Now, the finer you're focusing, it means the larger the beam has to be, which means your optics has to be larger. So then you're making your system larger in order to achieve smaller focus. In some systems that might be fine, in others not so. So that is a trade-off that you would have to work to say, if I make the focusing this small, it means the beam is larger because the divergence is larger. And the optics I need to, say I want to make it parallel, the optics to control that larger divergence, maybe I need more power. So I have all these different parameters I'll have to take into account. I cannot. So what this is telling me is I don't have absolute control over every parameter of the Gaussian beam independently. I can control the beam radius, but that is going to do something to divergence. Or I can control the divergence, but that's going to do something to the beam radius. These are inherently linked. Okay, and they are inherently linked also. So Z naught is a parameter. You can say that the beam is generated, and when it emerges from the source for a particular wavelength and for a particular omega naught, this divergence is inbuilt into the beam. And Z naught is a parameter that relates to that. Okay, so I hope the concept of Z naught is becoming clearer. Okay, so say I wanted a highly directional beam. I want to send, people have sent a beam, experiments long, I don't remember, decades ago was done, where they aimed a laser beam at the moon, and there's after the Apollo mission, a retro reflector was placed on the moon. So they sent a laser beam to the moon, and it reflected off that retro reflector and came back. I need the beam to travel the distance from here to the moon and back. Now, of course, the retro reflector placed on the moon is not 10,000 kilometers big. I'm putting a mirror, a finite sized mirror. So you might say, I need the spot size to be very small. But the beam has to travel this distance, and then for us to detect it back here, it has to travel all the way back. So there I have a trade-off. I have a finite sized reflector, so I want a small spot, but I have a large distance of travel, right? So then you have to see what is the divergence and the beam size. I have to manage them so they both come to acceptable values. Okay, and I can't say I want this theta naught and I want this omega naught and I'll get both of them. It's not possible. Okay. Okay, so if I wanted a highly directional beam, it actually means I have a small theta naught, a relatively small theta naught. How do I achieve that? What kind of beam should I have? What should my omega naught be? It has to be larger. So in other words, if I want a beam to travel a longer distance, I need a fat beam, which means I need larger optics, blah, 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 right? Okay. So just keep that in mind. Okay. So let's get to Z naught itself. So we have looked at, let me write this expression again. Okay. This is the beam waist at, and this we define as Z equal to 0. And if you go to a distance of Z naught, so this is Z naught, then we have omega of Z, which is root 2 omega naught. And we also said this is the point where you can imagine that the divergence becomes constant. So another way of considering Z naught is to say Z naught is the depth of focus of the Gaussian beam. Because you have this gradually varying divergence, and then it becomes this constant larger value, right? So this is exactly the same concept of depth of focus that we talked about earlier. Within this distance plus minus Z naught, or Some people may just say 2z0. So you can of course go z0 in this direction. You can move within this region and the beam behaves or has more or less the same behavior in this region. Therefore, I'll say this is the depth of focus for the Gaussian beam. What does it mean? If I look at, okay, let's say these are the wave fronts of the plane wave. Right? This should be equally spaced. What does the Gaussian beam look like? Well, if this was the beams, okay. These are all equally spaced, okay. What does the wave fronts look like for a Gaussian beam? It's going to look very similar over here. Why? Because zeta of z is tan inverse z by z naught. Okay. At the waist, z is 0. So at the waist, the phase is the same as the plane wave. There's no deviation from the plane wave. But as the wave propagates, this delay goes on building. So if the plane wave existed here, the Gaussian beam is delayed, so its wave front is going to exist a little delayed. Okay, I'm exaggerating it. It's not so delayed, but it's a little delayed. Okay. So wherever I expected the plane wave to be on the axis, the Gaussian beam is delayed, and so you'll see the wavefront crossing later. Okay. So this term, this zeta of z, is basically introducing a phase delay compared to how a plane wave would propagate. Does that make sense? Now, this expression was for what is happening on axis. But I have this term here. There is this term you clearly see is giving some curvature. So it's not, the Gaussian beam is not just, that's why I drew the wavefronts curved. So the Gaussian beam is not a delayed planar wave, right? On the axis, it is delayed from a plane wave in this way, but off axis, I have to take this into account. And this gives a curvature. There's no curvature at z equal to 0 because rho is 0 at z equal to 0. So this term doesn't play a role there. So there's no curvature there. So the Gaussian wave acts as a plane wave at z equal to 0. Okay. This is an important point, so we'll come back to this. So what we have done in today's class is started looking at the properties of the Gaussian beam. Okay, we've looked at the intensity, we've looked at the power, we've looked at the relationship between the inherent terms omega naught, z naught and lambda, and the significance of meaning of those terms. So z naught is the Rayleigh range or the depth of focus, theta naught is the divergence of the beam, and we've seen that we don't have independent control of these parameters. If you control one, the other one is going to change. Right? Okay. We're now finally looking at the phase. And of course, phase is all important because phase is what happens as the beam propagates and affects the propagation. It is why the beam has the behavior it has, because of its phase structure. If I want to change this beam and make it into another beam, I have to change its phase nature. Right? That's a lot of the work we do in the lab here, is to design and fabricate elements that change phase in a particular way and therefore control the kind of beam that you're generating. Why? Because that beam becomes useful for a certain application. You want to capture a cell and make it twirl around and twist around. I need a beam which has angular momentum. A regular beam won't have that. How do I control that? I make sure the phase of the beam has angular momentum. Okay, so phase is very important, and we've just started looking at the phase of the Gaussian beam to see how it's different or how it's similar to both that of a plane wave and a spherical wave. Okay.